All right. This is going to be on lesson 114. Lesson 114 is on graphing factored polynomial functions. It has a lot of information in it, so I'm going to break it up into a couple of videos. But the good thing is, at the end, it all kind of ties together, and it actually isn't as complicated as it seems initially. So first we're going to talk about the ways that we've graphed first degree polynomials. And remember that a first degree polynomial function is just a function in which the highest degree is a 1. So if we were to graph this, we could do just that point by point, make up the chart and graph it point by point, but we've learned some shortcuts. We learned that this is the y-intercept, so we graph the y-intercept and then just graph the slope from there. For second degree polynomial functions, which are quadratic functions, we also have learned a shortcut to graph these. So if we had something, something like this here, we would complete the square so that it was x minus some. This is a bad one because I put a 3 there, but let's just pretend that this is what it would come out to be if we completed the square with this. We know where the vertex of the polynomial would be by this point and this point. We could graph that and then pick just a couple of other points beyond that and graph the symmetrical thing. Well, we're going to learn kind of shortcuts like this for higher degree polynomial functions. A couple of things that we need to know in order to be able to graph them a little bit easier. We're going to need to learn about the number of turning points. We're also going to look at the sign of the highest degree term. Highest degree term. And then we're also going to look at the location or locations of the zeros of the polynomial. Okay, so those are the 3 things that we're going to be looking at, and then see how we can start graphing these higher degree polynomial functions. So the first thing we're going to look at is the turning points. Well, what is a turning point? A turning point is when you have a graph such as that. The turning points are the points at the tops of humps or the bottoms of valleys. And notice for the turning point, it actually goes from, it changes direction from going up to going down. Oh, here's another point. Or from going down to going up. So it totally changes the direction, okay? So those are the turning points. We're going to figure out how many turning points there could be in a higher degree polynomial function. These here points that are at the peaks, another name for those are local maximum points, and these points at the valleys are also called the local minimum points. We're going to use the turning point theorem to tell us how many turning points there would be in the function. The turning point theorem tells us that a polynomial function has fewer turning points than the degree of the polynomial. So, if you have a second degree polynomial function, also known as a quadratic, we know that they have the shape of a parabola, and it has 1 turning point. So I'm going to actually draw this smaller so I can put all of these together because we're going to use them. So for quadratic, second degree, down here, it has at most, or it will have 1 turning point. For a third degree, it will at most have 2 turning points. So that would be a third degree, also known as a cubic function. Or if we have a fourth degree, it could have a shape like this. It could have many other shapes, but at most, it's going to have 3 turning points. Excuse me. Okay, so that kind of tells us what the turning points. You know that at most, it's going to have fewer turning points than the degree of the polynomial. The next thing that we're going to take a look at is the degree of the highest term of the polynomial. The degree of the highest term, I wanted to leave these. The degree of the highest term is also called the dominant term because if you had, let's just say we had something like this. Oops. The highest term is going to be the dominant term because even if you take this term, it's going to be greater than the sum of all of the other terms in the polynomial as you get to very large negative numbers or very large positive numbers. So if we did, let's see, what do we want to do? We'll just say x is 10. So if x is 10, we would have 1, 2, 3, 4, 5 zeros. So that would be this first term. And then the sum of all of the rest of these would be only 11,000. And you can see just with the number 10 how much larger, how much dominant this first term is rather than all of the rest of the terms in the polynomial. So the degree of the highest term is going to be the dominant term. It's going to dominate what happens at very large negative numbers or very large positive numbers. So it's going to determine what's happening at the ends of these graphs as they reach positive and negative infinity type of thing. So let's see here. Okay, in bold it says the value of the polynomial for large absolute values of x can be determined by looking at the exponent of the highest degree term and looking at the sign of the coefficient of this term. So this graph of the second degree polynomial, we had this would be a negative x squared, and we could see with that as we got very large negative numbers, so say we had negative 10, well negative 10 squared would be 100, but then the negative sign in front of it, that would mean that as this continued on, it's going to get very large negative. If we had some positive numbers, as we get into very large positive numbers, again, when you squared that would be positive, and then the negative sign in front of it would make that continue to be very large negative numbers. So it's going to continue smoothly down negatively on both sides of that equation. If we look at this one, this was, what did they have? They had y equals x cubed minus 3x squared plus 5. Whoa, sorry. All right, so if we looked at that one, we see that for very large positive values of x, so if we were coming over here, very large positive values of x, as you cubed a very large positive number, that's going to become a very large positive number. So as you get very large numbers, you're just going to continue going up positively. If it was a very large negative number and you cubed it, well, when you cube a negative number, it's going to remain negative. So as you get very large negative numbers, that's going to continue on negatively. For okay, let's see, for this one here, for the graph of the quartic function, just like the parabola, it's either going to open upward or down, just like the parabola. because if you have a very large negative number and you raise it to the fourth power, well, that's going to become positive. So even as you get to the very large negative x values, it's going to become positive, very large, and then the same thing for the very large positive x values. As you raise them to the fourth power, that's going to become very large positively as well. Okay. So now let's look at the general cubic equation. General cubic equation, I think I can erase all of this now. Okay. So the general cubic equation would be f of x equals ax cubed plus bx squared plus cx plus d. All right. Let's see. The graph of a cubic function can have a flex point. So it can either have a flex point or it can have a flex point and two turning points. Okay, so what would that look like? Actually, let's first talk about what is a flex point. So a flex point is actually this one flex point. It is something that looks like this. And this would be the flex point here. This is different than a turning point because this isn't changing direction. This was going positive. Here, it's still going positive. So it's just an area where it kind of changes from being maybe you can say going from convex to concave. That's one way to kind of think about it. Or you can kind of think about it as being from face down to face up. But that's what a flex point is. So this cubic functions, they can have one flex point, or it can have a flex point and two turning points, such as this. Well, where are the turning points and where are the flex points? Here's a turning point because it's going from going up to going down. Here's a turning point because it's going from going down to going up. And the flex point would be somewhere in here. Where it's kind of going, it's still going down, but it's kind of going from face down to face up at some point. So it can look like that. It can also look like this, where it has just a flex point, or it has two turning points and a flex point as well. Let's see, it says the shape of the graph is determined by the values of the coefficients of A, B, and C, and then its vertical position can be changed by D. So this kind of like that constant at the end that was the vertical shift for the other graphs that we've already looked at. All right, I think I will go on to the quartic function and then we'll end this video and start another one. So let's look at the next thing, the quartic function. Quartic just meaning that its highest degree term is a 4. So if we had y equals ax to the 4th plus bx cubed plus cx squared plus dx plus e, again, these coefficients are going to affect the shape of the graph, and then the e is going to affect the vertical position. For this here, if a is a positive number, the graph is going to have any of these shapes. It could actually look like a parabola. It could look something like this, and we'll kind of review these. Oops, I don't think I wanted to do that so much, sorry. That actually is a turning point. There we go. right, so let's take a look at all of these here. So if the a term is positive, because this is raised to the fourth power, that's an even number, no matter what the x value was, whether it was a negative or a positive, when you cube it, it's going to be positive. That's why every single one of these will open up. It could have just one turning point. It could have one turning point and two flex points. It could have 3 turning points and 2 flex points, or actually no, these are the same. 3 turning points and 2 flex points. If the a term, if the coefficient a was negative, just like that negative x squared, these would all be flipped and would continue on negatively in both directions. Again, the constant e is going to affect the vertical position. So this kind of gives you an idea of the shapes of cubic and quartic functions as well. Let's see. Now this last part is fun. This last part they mention, and then I didn't see anything in the practice on it, but we will kind of look at this here. Let's see. It says, the sum of all real and complex roots is negative b over a, and the product of all real and complex roots is k over a. If the degree of the polynomial is even, and is negative k over a if the degree of the polynomial is odd. So the average of all roots, so the average of all